See, there we, there we go. Okay. So as I said, the moons of these gas giants um, can be pretty spectacular. So Saturn and Jupiter have over 50 moons each. Some of them are very big. Ganymede is the biggest moon in the solar system. It's much bigger than our own moon. And they all have different features, and you'll notice they look differently. So these are, I believe, the four moons of Jupiter that are visible through a telescope. And there's a lot of fascinating things about the moons, and because, even though they're smaller than planets, because of their interaction with large gravitational bodies, they're going to be able to, in some ways, appear to be geologically active, but not in the same way that we'd say a planet's geologically active. Their insides are able to move, but they aren't. Like I said, it's one of the mysteries we'll have to think about as we go forward. So small moons are moons that are less than 300 kilometers big. There's no geological activity. They're barely spheres. Medium-sized moons are 300 to 1,500 kilometers big, and they would have exhibited some geological activity in their past, much like our moon. But large moons, which are still smaller than planets, can have ongoing geological activity, which is interesting, and we'll see how that works. Again, remember that these are orbiting giant planets, so that gravity is going to play a role. Now, medium-sized and large-sized moons. So you'll notice that Jupiter has 4 very big moons, and Saturn has 1 giant moon and a bunch of medium moons. Jupiter probably has a lot of medium moons too that we just don't look at. Uranus has 5 of these medium moons. Neptune has Triton, which is sort of on the cusp of being a large moon, and it's got this little tiny one. Compare it with Mercury and the moon and Pluto. So you'll see that a lot of these moons of planets are indeed actually bigger than Pluto, and you can see that several of the moons of Jupiter and Titan are bigger than our own moon, and some are even bigger than Mercury. And we're going to have to define a planet very carefully, which we'll do in the next chapter, to understand why something that's bigger than a planet would be considered a moon, right? So I can sort of give that away. A planet must orbit a star, right? Ganymede is bigger than Mercury, but Ganymede does not orbit the sun. It orbits Jupiter. Jupiter orbits the sun. So that's the first criteria of being a planet. You must orbit your host star. Again, many numerous than the medium and large moons. There's not enough gravity to be spherical, but you can notice there are all these tiny little moons, right, that go around. Some of them are very small, some of them are pretty big, but they're all in that small moon category. And there's many, many small moons. So Jupiter's what they call Galilean moons, and these could be viewed with the Galilean telescope. Why are they geologically active? So that's interesting. These are all smaller than, Ganymede's about the size of Mercury, but these are all smaller than Mercury. You'll notice the moons all look different, and there's a lot of geologic activity. And if size is what we talked about, the main factor as far as geologic life, how can these be geologically active? Well, let's first they're geologically active because we observe them to be geologically active, right? Io has volcanic activity. And Io, in fact, not only has volcanic activity, it is the most volcanically active body in the entire solar system. All right, you can see these spots here. And they're even calling it hot lava flowing out over sulfur dioxide frost, causing it to sublimate explosively into gas. You can see these explosions here on Io. And you can see the lava in Io. So not only is it volcanic, it is incredibly volcanic. And the volcanic eruptions continue to change the surface of Io. Now, what leads to this is basically this idea of tidal heating. So you'll notice that the planet, as it moves, gets sort of squished and squashed as it orbits. And that stirs the pot of the stuff inside. So basically, it's a small cup of coffee, but when as it orbits Jupiter, it's got a stirring rod to keep it, it's got like a heat source to squish it and get everything moving around, which lets it heat up and remain geologically active. So in some sense, small moons that are orbiting these large planets can remain geologically active longer than planets. We can see that Io already has. There's also this idea of orbital resonance, which is that you have these moons, right? Io, Europa, and Ganymede. They all are sort of locked in with their orbits, so that keeps a certain tug happening at the same time. So you can predict it, and then because it adds up, it creates this resonance which keeps the insides of the planet moving. And every 7 days, the 3 moons line up, so they whiz around Jupiter very quickly. So even though they might be geologically active longer, you're never going to have stable climate if you're whipping around that quickly. So Europa's ocean, it may have this underground water world. There seems to be evidence of water seeping out, or at least water vapor seeping out. These ridges that are observed are thought to come from water, but it's thought that the liquid layer is underneath this solid layer. And let's see here, Europa's interior, you'll notice that it has a rocky interior, a core, a metallic core, much like Earth. And you'll notice that the water layer is very thin and covers the whole planet. Now, what's interesting is it's often thought there are hidden vast amounts of water even under the Earth, little layers like this, little pockets of it. And we can see the rising plumes of warm water that sometimes create lakes within the ice of Europa. And the surface terrain is indicative of sort of icebergs being suspended in place. So Ganymede, largest moon in the solar system, there's clear evidence of geological activity. There's grooves, there's young terrain, which means volcanic activity. There's old terrain, right, that's heavily cratered, so we can tell the difference between the two. And tidal heating plus heat from radioactive decay, it's going to make Ganymede an interesting big moon, if you will. So let's see if we see more pictures of it. Nope. So Callisto is your classic cratered ice ball. There's no tidal heating, no orbital resonance, but it has a magnetic field. And the question is why? It's one of those things that you would expect it not to, because it sort of looks like a dead moon. But it does have a magnetic field, and there's no really good explanation for it. So those are Jupiter's moons. Now we're on to Titan's moon. Now Titan's moon, or Saturn's moon, Titan, actually has an atmosphere. So it has its own atmosphere. It's actually similar to Earth's in that it's mostly nitrogen, but there's no oxygen. And instead of solid rocks, it's mostly solid ammonia. So Titan has a thick atmosphere. It consists mostly of nitrogen with some argon, methane, and ethane. So it would smell bad, and the water would all be alcohol. So you could get drunk and smell bad on Titan. But we can see into Titan's surface. One of the reasons that we send so many probes and concentrate on Jupiter and Saturn is because there's also interesting moons to study. And the Huygens probe provided the first look at Titan's surface in early 2005. It had liquid methane rocks made of ice. And we can see this 1 kilometer, this sort of large surface. And we can see right here on the surface of Titan. That's the surface of Titan. That's crazy, right? So we have the whole moon. We have this valley of these ridges. And then we landed right there. Titan's lakes. These might be liquids, might be lakes of liquid methane. Probably doesn't smell pleasant. And of course, the medium moons of Saturn, you have Mimas, which is often called the Death Star moon, right, for all Star Wars fans. But you'll notice the medium moons are there, and they're big, but they don't have, they almost all show evidence of past volcanism, but without that orbital resonance, they just don't have the they're a lot like our moon. You'll notice they all look exactly the same. Okay? So they had evidence of these things, but they're geologically dead. So ongoing activity in Enceladus. So Enceladus there's fountains of ice particles and water vapor from the surface that indicate geological activity still ongoing. So Enceladus is a small moon that has some stuff going on, and it's right there. And interestingly, it's the smallest of these small moons or medium moons of Saturn. So yeah. So these are, sort of what's going on with the moons of the gas giants. Neptune has a big moon, Triton. It's similar to Pluto but larger, and it has evidence of past geologic activity. And that's one of the things is Pluto is thought that it might be an ejected moon of Saturn or Uranus, which is another reason to take away its planet status. But again, when we look at Triton, it's very similar to, or it could be that Neptune captured Triton, and Triton originates from elsewhere in the solar system. So again, we're looking at geologic activity. Rock and the metals melt at high temperatures. But remember, the Jovian moons are mostly hydrogenic, so they liquefy at lower temperatures. And so if the tidal heating can melt internal ice, that can drive that activity. So if we could just figure out how to, live on some sort of Jovian moon, we could live there for a while. And then, of course, we have rings. So each of the gas planets has rings, but only Saturn's are really spectacular like this. So that's why we start with Saturn. And it's thought that Saturn's rings are not that we just happen to live in this time, that they're not a permanent feature of Saturn, and that in, I think, as little as like 500,000 years, they might disappear completely or settle back down into another moon. But Saturn's rings are not continuous, right? They're made up of these little tiny individual clumps of dust and rock and ices, and they orbit over the equator, and they're very thin. All right, and you can actually see that these tracks are other moons sort of clearing out debris in the rings. So this is a close-up view of Saturn. I think you can see one. This is from Cassini, that I think in these gaps of the rings, little moons or little rocks traverse and push it out to the side. Yeah, we can see one right here moving through. And it sort of moves and ruins it like a record player. So that's what the rings are, but you'll notice that Jupiter has rings, Uranus has rings, and Neptune has rings, right? You can see Saturn here. So all these gas giants have rings, but the other ones are thin, and there's always this particulate, sort of their own dust system going around them. But Saturns are really spectacular. So, and again, they're all sort of the same, these thin layers of icy rocks and things like that, and dust. So we've seen that. And it says, why did the Jovian, they form from dust created in impacts on moons. They also might be created, the rings aren't left over from planet formation, we know that, but they may also be not just impacts, but geologic processes on the moons. So it says the most likely source is impacts with Jovian moons, but it's also very likely that continuing expulsion of particles from Jovian moons contributes to these ring systems as well. All right, and they're talking about how the ring formation is a lot like solar system planet formation. And they mentioned that Saturn's would be an accident of our time. Okay, so moving on, we want to move on to sort of the less exciting objects, but in some cases the most deadly in our solar system. So we will be talking about, of course, asteroids, comets, and dwarf planets. And we'll hopefully be able to talk about the criterion by which Pluto does not keep its planet status. So let's go. Oh, I have to stop sharing this one. Okay. So, okay. So now we want to look at the smaller bodies in the solar system. We want to look at asteroids and comets. So asteroids exist in the inner solar system. They're mostly made of rocks. Oh, my little pointer is not here. They're mostly rocky, and they can we can spot them in telescopes because they move much faster relative to the background objects in the solar system. What that means is that over long exposure times, you get a nice thin line like this, and that's how you can spot one. And then we have comets. Now, comets are generally larger, and they're usually in the outer solar system. And these tails, which are usually associated with them, this is a common misconception, comets, for the most part, don't have tails. They only get tails when they get deflected into the inner solar system. So when they come near the sun, then they start to have a tail. But the tail is only something they have part of the time. And the tail also indicates not which way they're moving, but the direction of the sun relative to them. And we'll see that in a minute, talk about that. And then there's dwarf planets. Right? So dwarf planets are sort of super large comets, and the discovery of more dwarf planets in what we call the Kuiper belt, which is like it's like the comet belt outside of Neptune's orbit. But understanding the structure of our solar system required us to revise the definition of Pluto. So if we kept Pluto a planet, we'd have to add at least a dozen other objects that are similar size, and possibly 50 or 60 in the future. So the discovery of Eris, which is, I think, even a little bigger than Pluto, led to the reclassification of Pluto as a planet. And there were just it was easy to do as far as creating 3 criteria in which you use to describe planets or to define planets. So now, meteors and meteorites. So a meteor is the flash. So these are Earth-based terms, and you'll notice these are kids touching the rock. I don't know if you've ever been to the Museum of Natural History. Probably no one's going lately, but it's certainly, you can become friends with a meteorite. So a meteor is the flash of light produced as a small object enters the atmosphere of Earth, and then the meteorite is the object once it falls to the ground. So that's some common terms that you'd hear. And so now we're gonna break down, and we'll have a little bit of section in between all of these. So we're gonna talk about asteroids. All right. So we want to know what they are, what they're like, and I think we talk about what we have to fear from them here. So what do asteroids look like? Well, asteroids don't become spherical. They're held together by gravity, but you'll notice they're very tiny, and they orbit the sun. So they don't orbit planets. They can cross planets' orbits, but they generally orbit the sun themselves. All right. So they're the rocky leftovers from planets. The largest, Ceres, is known as a dwarf planet. It's the largest asteroid. It has a diameter of over 1,000 kilometers, and this is the largest asteroid in the solar system. But by calling Pluto a dwarf planet, it allows us to classify Ceres also as a dwarf planet. But it's not just because of its size. All right, Mercury's pretty small. We're going to see that there are other classifications as well to get this dwarf planet fact. There are about 150,000 listed asteroids in catalogs, and probably over 1 million asteroids that would have a diameter greater than 1 kilometer. Why is that important? Because asteroids that have a diameter that high, if they're in a near Earth orbit, that's when they start to become problematic if they are on a collision course with Earth. But most asteroids are not on a collision course with Earth. The number that are pretty small. At least they're not millions and millions. Smaller asteroids are much more common than larger asteroids. And all the asteroids in the solar system wouldn't add up to even a small terrestrial planet. So even though Ganymede's pretty big, or not Ganymede, even though Ceres is pretty big, if you put that together with all the other asteroids, you wouldn't even come up with Mercury, just the smallest terrestrial planet. So it's really just the leftover scraps. We've got some interesting close-up views of asteroids here. You can see that they have their own little impact craters, so smaller things can still hit asteroids. Some of them even have their own little moons, which I thought we were coming here. But here's Ceres from the Dawn probe. It says a mysterious bright spot, but it's probably just a reflection of salt or other mineral deposits from an impact or something else. There's a 4-kilometer tall mountain that rises above otherwise bland surroundings. It offers no clue to its origin, but it's there. And so that is a no. Anamana is from outside of the solar system. So that is a strange object whose orbit was parabolic, not elliptical, which proved it came from outside the solar system and got flung further outside the solar system. Yeah. So let's see here. Yes, interstellar. Not the movie, but that's the term. It's from another star system, and it's going to another star system. And pass through ours briefly. Okay, so asteroids can't have moons. So the asteroid Ida, which is only 10 kilometers, that's smaller than the island of Manhattan, right? Has a little moon called Dactyl. Poor little Dactyl. Can't seem to get away. But again, it's not an asteroid because it doesn't. It's interesting. It's not an alien spacecraft, but if an object were to look like an alien, it looked like what, it was a big rectangle, which is about what if there were a large alien spacecraft in a similar orbit, it would look a lot like Amoana. But no, it was probably just a very strange rock. But its shape was very odd, that's for sure. We have again here, most meteorites are just pieces of asteroids, or they're small asteroids themselves. And meteorites help us understand the age of the solar system. I don't want to spend a lot of time getting bogged down on this, but basically you can look at processed asteroids or meteorites and primitive meteorites. So primitive ones are unchanged in their composition since they formed 4.6 billion years ago. Processed ones are usually thrown off from planets or moons. So for instance, you can actually find Mars rocks on Earth from impacts on Mars, and vice versa. You're likely to find Earth rocks on Mars from impacts. Like when the asteroid that killed the dinosaurs probably deposited some rocks on Mars, for sure. You can see what they look like, the primitive stony asteroid versus a carbon-rich. These are the primitive ones. And I think we can see some processed ones, that are mineral-rich and, are the result of geographic processes. So we talked about that. Why is there an asteroid belt? Basically, Jupiter. Jupiter has what I like to call, you have the asteroid belt in between Mars and Jupiter, and it's pretty stable from the inner planets and Jupiter itself. But Jupiter has these Trojan asteroids, which sort of are, I call them Jupiter's groupies. So you have these ones are getting pushed away, and these ones are chasing after it. And those will interact with other asteroids and keep things, for the most part, stable in our inner solar system. Now, that being said, Jupiter also occasionally kicks things into the inner solar system. So while it's kept us safe from being completely bombarded, it very likely kicks in the meteors that will eventually lead, or the meteorites or asteroids that may lead to our eventual destruction. So let's go out here. I like these thought questions. Orbital resonances. So orbital resonances apply to these asteroids with Jupiter. And eventually these nudges will move the asteroids out of the resonant orbit, and this can leave gaps in the belt, but can also, fling the asteroids toward us. I think the asteroid belt is just stuff that, again, remember what we said, it's not, there's not enough asteroids to form even a small planet inside. So I think it's just the stuff that's left over that just gets stirred up by Jupiter as it goes through. And Jupiter's influence is the big driving force behind the asteroid belt. That should bring us to comets. So we want to understand why comets grow tails and look the way they do, and we want to understand that statement I said earlier, and unpack it a little bit of why comets. I say most comets don't have tails, and why they're mostly associated with outer solar system objects. Okay, so let's see here. Why do comets grow tails? That's the first thing we're going to look at. And you'll notice, like I said, well, you won't notice here, but the comet, the tail is not indicative of the direction of travel of the comet. It's indicative of the orientation of the comet in relation to the sun. So let's look at these comet facts before we move on to, right, that'll tell us. Okay, good. So before we look at where that tail comes from, comets are formed beyond the frost line. Again, they're bigger because they have that water, those hydrogenic water, ammonia, and methane available to them to form their cores. The nucleus of the comet is like a quote-unquote dirty snowball. Comets, again, don't have tails unless they get into the inner solar system, but most of them remain perpetually frozen in the outer solar system, so they'll never get tails. And you have to get into the inner solar system. So let's take a look at that. You'll notice here we have a comet, that the comet's motion is moving this way, right? But the tail is moving this way. So the tail, so the sun is basically right here. I could have done that better with a better color, but I don't draw that much in this class. Here we go. No, it didn't change. All right, so the sun would be right here, yellow. Now the rays of the sun represent the solar wind. And so as this comet gets into the inner solar system, all that stuff, the ices, it gets hot and warmer. So all the ammonia and the water can heat up. And when it heats up, it starts to off-gas. So, and you actually have two tails. You have a plasma trail that gets ionized. That's stuff that gets ionized right from the sun and goes through. And then you have this gas coma, dust particles that will be sort of a combination of the, mostly influenced by the sun, but partly influenced a little. That's why it gets this curve structure by the comet's motion. So the sun heats stuff up and ejects the dust and plasma, and that's where the comets get its tail from. So it all has to do with its orientation to the sun, not its motion. You'll notice its motion, there's no tail there. Remember, there's no atmosphere in space, so it's not moving against air or anything. Otherwise it would have a tail, much like a boat leaves a wake or something like that. So that's where it can be counterintuitive and seem a little different. Let's see, going through more stuff in the solar system. You'll notice the nucleus looks like a bit like an asteroid and is about the same size. It's just the composition is what makes the comet. So coma is atmosphere that comes from heated nuclei. The plasma tail, so that's this part. The plasma tail is gas escaping from the coma, which is pushed by the solar wind, so it's in a direct line of sight. And the dust tail is pushed by the photons. So remember, light can exert pressure on things. I'm not sure if we saw that. I usually show that in class, but light can impart momentum. And you can prove this in a lab very easily. That's not just guesswork. If you see those windmills, they have them at a science museum sometimes, where when you shine light on it, it moves faster. So a comet's tail growth, this sort of makes some sense. Out here in the outer solar system, right, the comet is just a ball of ice. So the gas coma begins to form as we get closer, so it'll become brighter. And then as we get here to the sun, right, the sun creates the tail, and as our orientation to the sun changes, that tail will change direction, but the gas will get flung and accelerated. And so you'll notice we see that here, but the plasma tail, which is the brightest tail, will always form the opposite of the sun, and then we brighten, we lose the tail, and we become a solid sort of ice ball again. All right, but you'll notice that comets have very highly elliptical orbits. All right, very, very, very elliptical. All right. So the Rosetta mission happened very recently. In 2015, I remember when this they launched a probe into a comet. It sent to orbit Comet 67P as it approached the sun, allowing us to watch the process of a comet growing a coma and tail. So that was pretty exciting. You can see it in the pictures there. Now, comets eject small particles that follow the comet around in its orbit and cause what we call meteor showers when the Earth crosses through the comet's orbit. So usually you can predict when these meteor shower events will happen because we can see the Earth's position relative to the comet, just close to the Earth. When we pass through that dust storm, we see it, and they can be pretty spectacular. Again, comets come from the outer solar system. So comets mostly come from the Kuiper belt and the spherical region of the solar system called the Oort cloud. But the Oort cloud contains many, many objects that are of all sorts of varying size, and they very rarely will come into the solar system. Very, very rarely. Their orbits would be large. Keep in mind, it takes Pluto about 240 years to orbit the Earth. It takes Eris about 560 years. So you're talking thousands, if not tens of thousands of year orbits, and those orbits may not even bring them close to the inner solar system. All right. So how did they get there? Again, it's just leftover stuff from planet formation. So now we want to get to and talk about these dwarf planets and understand what they are about. Okay. So we want to see why we classify Pluto as a dwarf planet and why Pluto is seen as more of a comet than anything else. And dwarf planets in the Kuiper belt really are sort of seen as these large comets. So first, let's talk about Pluto. And this was very exciting when this New Horizons mission first came to Pluto. And it was the first time we got detailed pictures of Pluto. It was really, really exciting. I remember when I was at LaGuardia. I mean, these pictures were taken when I was working at LaGuardia, and we were all very excited about them. It was a very big deal. So one of the things that makes Pluto's orbit different, or makes it not a planet, the other planets orbit in what we call the plane of the solar system. So Neptune, along with all the other planets, has very little deviation from the plane of the solar system. Pluto, on the other hand, Pluto is tilted, and its orbit comes within Neptune. So for a while, from 1979 to 1989, Pluto was not the farthest planet from the sun, or object. It was closer to the sun than Neptune. So so it's got this weird tilted orbit, and it's not in the plane of the solar system. It orbits in this 17-degree tilt. Okay, so that makes it very different from the other planets already. It has a moon, Charon, that's nearly as large as Pluto itself, probably made by a major impact. So is it Charon-Pluto or Pluto-Charon? Hard to say. Of course, Pluto is very cold, and it has a thin nitrogen atmosphere that refreezes onto the surface as Pluto's orbit takes it farther from the sun. And New Horizon has revealed a geologically active surface with mountains made of ice and far fewer craters than expected. So our picture of Pluto is different than we thought it would be. And the fact that there is some geologically active surface means it might probably interacting with something else, keeping it active, which confirms that it's not a planet. So it's much smaller than the 8 major planets, all right, than the non-dwarf planets. And it's not a gas giant like our other outer size stuff. When you look at its composition, it looks more like a very large comet. It's elliptical, its orbit is not in the plane of the solar system, and it has, like I said, it has a lot more in common with comets than it does planets. However, one thing it does have in common with planets is it does have a system of its own, but you really have Pluto and Charon probably orbit each other, and then you have Styx, Nix, Hydra, and Erebos, these other things. It's hard for me to think of Charon orbiting Pluto because you have to orbit the center of mass. This is one thing I never understood about the Pluto-Charon system. It's always represented this way, but really these two should be orbiting around each other if they're nearly the same mass, orbiting around a point. And then it makes sense that these could orbit around the Charon-Pluto system. But when they lift the covoid thing, I'll have to ask Professor Tan or Professor Sheffield about that. I've always wondered about it. But our evolving view of Pluto, right? So in 1930, that was our picture of Pluto as a spotted object. In 2010, the Hubble took the image of Pluto, and this was, up until 2015, this was the image of Pluto. This is what it looked like. Now, with New Horizons, we have a much clearer picture of Pluto, an up-close and personal view, which is incredible. It's very exciting. And what did we see? So again, like we said, it has revealed a much more active geology than expected. So we can see here that these mountains are as tall as the Rockies. So it has its own like Rocky Mountains, and they're probably made of water and ice. And even at 40 degrees above absolute zero, nitrogen ice can flow. So we see these flowing clouds of nitrogen, which may cause erosion. So we were also able to look at Charon, and it also shows evidence of recent geologic activity. You can see smooth regions resemble the lunar maria, suggesting the eruption of lava, which in this case might be water. It wouldn't be hot lava. But yeah, I mean, hot relative to the surroundings. So it might be, like I said, it might be that Pluto and Charon are geologically active because they orbit around each other. That would make sense, really, when you think about it. But I don't know. That's just, I was just thinking about that. And so we know a little bit about the Kuiper Belt, but we don't know much. We want to get new telescopes, particularly James Webb, that can reflect more light and see objects that are very dim in our solar system. But the objects are expected to look similar to Pluto, and New Horizons will visit another Kuiper Belt object in 2019, which it did. It's probably processing images. And I think this mission goes on for a while, the New Horizons. So hopefully we'll see some more stuff. But Pluto is not a planet. We didn't talk about another aspect of Pluto. It doesn't clear its orbital. It does not. It's not just its size. It is small, but it orbits outside the plane of the solar system, and it doesn't clear its orbital neighborhood, which is the big hurdle. Because its orbit could potentially be affected by interacting with other Kuiper Belt objects, so it's not clear like how to define these things. And then again, like I said, we found other Kuiper Belt objects, which I thought there was a slide about the other Kuiper Belt objects. Let me see here. Because we have Eris, there's a bunch of them. Yeah, no, they seem to have changed that since I last did planets. So Pluto is not a planet, right? So let me look up here. I thought they talked about in the version I used to do this. They talked about it extensively. Criteria for being a planet. I feel like I'm missing one. So right, you have to orbit around the sun, which Pluto does, but not in its plane. So that makes it half and half. It has to have sufficient mass to assume hydrostatic equilibrium or round shape, which Pluto does. It clears that criteria. And it has to clear its neighborhood around its orbit, meaning it has to get rid of all the stuff. And I did say that in its orbit. Pluto orbits around the sun, even if it's not in the plane. It is a sphere, but it is not. It does not clear its own orbital neighborhood. So therefore, Pluto is not a planet. So very sad. Pluto's not a planet. But again, I want to go over a list of, hold on, large. Let me see. I don't have a slide for them, but I can tell you what they are. Large Kuiper belt objects. So if we look here, if I'm looking at this. So Pluto, so there are, in the Kuiper belt, Eris is bigger than Pluto, and it's got its own moon. But there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 other objects that are smaller than Pluto and Eris, but not a whole lot. They're big. They're big objects. So, you know, and they have the same properties of Pluto and Eris. So if you call Pluto and Eris planets, the total number of planets in the solar system now has to jump to 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 already. And raise your hand. I can't see you, but raise your hand if you want to memorize, make poor children memorize the name of 21 objects. I didn't think so. Yeah, Martin. Oh, right. Oh, I see. Gotcha. No. My fault. You're right. I asked you to raise your hand. There's a button for it. I get you. But making those poor kids memorize everything would be not very nice. So now I just want to very briefly go over killer asteroids. Basically, cosmic collisions, small bodies versus planets. So impacts are a big issue, and again, it's thought that it's assumed that an asteroid killed the dinosaurs, but it's only really, that's the only one really clearly linked to a mass extinction. There is a scientist who argues, I think a little convincingly, that it's a coincidence that asteroid hit when there was a TRAPS event going on, because almost every mass extinction has been coincided with the TRAPS event, not necessarily a major impact. That's when a large area is very volcanically active, like we're talking the size of Texas, or a very large, like more than a supervolcano, like a series of supervolcanoes exploding for continuously for like tens of thousands of years. It's not good. But the fossils record indicates that there was certainly that extinction, but with the fossils disappearing below that line, which I'll show you here. These are impacts with Jupiter of several comets, but mass extinctions. You have this this layer here, iridium layer, that was certainly spread by the asteroid, and again, dinosaur fossils appear below it. Nothing appears above it. So there's good evidence. It's a controversy. It's not one way or the other. It's it's a problem looking for a solution. But with that said, impacts can certainly affect life on Earth, and they can certainly change the features of planets. But we already sort of know that. So good. We finished the solar system on time. Well, we didn't finish the solar system. We've talked about the objects in the solar system, save one. And we want to introduce it really quick. I think we will we'll stop. Well, I'll stop talking at about 6:30 or so, and I'll stay in the room till 7 so that we can you can do the activity, and if you have questions, you can work on it and watch the videos. In fact, yeah, it's about 20 minutes of video. I might stop earlier. In fact, you know what? I'm going to stop now because we're at the end of this chapter. And so what I want you to do, because we have our telescope activity, so I'll record while I explain the telescope activity so you can refer to that instructions. So what you're going to do is you're going to go on Blackboard, and you have your list of 4 activities. You're going to download the one that says Building Galileo's Telescope, and you're going to read that to get an idea of what we would have done in class. It's not that big of a deal, but it'll give you an ideas of things to look for when you watch your 2 videos. So the first video you're going to watch is actually someone building the telescope, since we can't do it in class, and hopefully they'll be able to show you some results, and hopefully their telescope will work, whereas the one we build in class almost certainly wouldn't. And then I put up another, and so that video is about 10 minutes, and then there's another video that's about 10 minutes in length too, and that one is about the James Webb Telescope. And so you can sort of see the first telescope and the most scientifically advanced telescope being built today. And so basically using your, you know, I want you to learn about that, think about it, and you know, take some notes about what you've learned, and then use the prompts from the, you know, there's in writing the activity instructions or the lab reports or whatever I call them. Use those to guide you in writing you know, your 1-page single spaced, or if you're going to do double spaced, you know, 2 to 3 page paper. And yeah, and please have separate paragraphs. That's something. I haven't graded yours yet, the first ones, but I'm going to get to that probably soon, probably by the beginning of next week. Yeah, just you need several paragraphs. That is important. The guideline, everything is on Blackboard. Everything's on Blackboard. So just look through the stuff that's there, and you should find them. Okay? And also take this time now, because I do want to do this during class, since I have you all here. Now is an excellent, excellent time to do a little research on the space missions too, and see which one you might want to write about. And again, don't email me your answer. Turn it in like it's an assignment on Blackboard, because I'm just going to go through them and assign them tomorrow, and then post your official topic Wednesday. You won't have your topic till Wednesday, but just give me your top 4 choices, and we can do that. So I think I want to give you that time to do that, since I have you all here on the computer, so that you can be sure to get that done. And this way you can get it done. You don't have to worry about whether you did it or not, or extend even more time. So actually, I think that is a better use of time. So I'm going to stop recording.